Okay, I've got some examples to go through with you to practice rational function graphing and look for important features. First one here is 2x over x squared minus 4. So no particular order to the way that I'm going to do this, but let's see here. The x-intercept is the value when y equals 0. Because this is a fraction, if I'm setting it to 0, like this, the only way that happens is if 2x equals 0 and therefore x equals 0. So there's my x-intercept. I'm going to keep a table of values to keep track of some things that I'm finding out. So x equals 0 at y equals 0. Well, then that's going to be the y-intercept as well, isn't it? Now, let's look at the vertical asymptote. Vertical asymptote occurs when you divide by values that are 0. So it's x squared minus 4, which factors into x minus 2 and x plus 2, set equal to 0. This produces x equals plus or minus 2. So let's put this here, and we'll write undefined, and at 2 we'll write undefined, and we'll put them on the graph as vertical boundary lines. Now the horizontal asymptote, that has an equation of y equals. We look at the terms here, x to the 1, x squared, and 4. We're going to divide everything by x squared, the largest degree term. I would end up with 2 over x as a numerator, 1 on the denominator, and 4 over x squared. That's after dividing each term by x squared. Imagine x being really large. We can say it approaches infinity. 2 divided by something very large is 0. 1 is 1, and 4 divided by something large squared is 0. 0 divided by 1 gives me the horizontal asymptote y equals 0. So I'm going to make a dotted boundary there. Now I'm going to label all these. Y equals 0, x equals 2, x equals negative 2. Okay. I should also plot that value that I know, the x-intercept. Alright, at this point, I'm just going to fill in the table with a couple of other values so that I can be as clear as possible about what's going on. Negative 3. That makes a numerator of negative 6 and a denominator of 9 minus 4, or 5. So negative 6 over 5. I'll just estimate. Negative 3, negative 1, and a little bit more. Now, because of these dotted asymptote boundaries, I know this is going to have this general sort of shape here. It's going to head toward that asymptote, and actually I don't like how I did that. I'm going to redo that. It's going to head toward this asymptote and toward this asymptote, and put little arrowheads on the end. Let me check positive 3 while I'm at it, because often there's symmetry. This is 6 over 5, so it is symmetric. It's the same number, but positive this time. 1, 2, 3, a little bit more than 1. Again, because of the asymptotes here, I'm going to plot a smooth curve heading toward these boundaries with arrowheads. Okay, now I just got to figure out what's going on in here. I've got one point, but only one point where it crosses the axis, and I know I have 2 boundary lines that I have to get near to. Let's substitute negative 1. Numerator negative 2, denominator negative 3. So that's positive 2 thirds. A negative divided by a negative. So that's going to be right about there. Positive 1, now I get positive 2 over negative 2 thirds. So you'll notice that this particular function, because of the square and then this being linear, it gives us some interesting symmetry between the numbers. So that's right about there. Now, we're not going to plot a line here. This is not like this. Okay, this doesn't show asymptotic behavior. What we're going to do instead is we're going to come from up here, very near to the curve. We're going to swoop in here through these lines and then swoop back like this. That's what we should be graphing. Now I'm going to check it on my graphing calculator. And I've already got this one entered right here. I think that's the same function. 2x over x squared minus 4. I'm going to choose zoom 4. That's often a good window to choose. And as I look at that, it looks just like that sketch. Sure enough. Good. Okay, that's it basically for that one. Let's move on. Let's try this one. X squared minus 4 over x squared plus 1. Okay, now this time, x-intercept, or y equals 0. Remember, that's where the numerator equals 0. This factors into x plus 2x minus 2. And so I get the intercepts of plus and minus 2 for x. Let's make a chart of values like I did before. And let's have negative 2 with the y value of 0. Negative 1, 0, 1, 2, and 2 has the y value of 0. And I'm probably going to choose those other values here to just make sure I see what's going on. Let's plot them as well. Next, let's think about y-intercept. The y-intercept occurs when x is 0. So these are just going to drop right out of the analysis here. I'm going to have negative 4 over 1. So 0, negative 4. All right, let's plot that. 1, 2, 3, 4 units down, right there. Vertical asymptote. The vertical asymptote happens if I divide by 0. So I'm trying to solve x squared and 1 equals 0, which leads to x squared equals negative 1, and something squared can never equal negative 1. There is no vertical asymptote on this particular rational function. The horizontal asymptote, largest degree term is x squared. I've got 2 of them. So if I divide all terms by x squared, I would have 1 over 4 over x squared. Write that a little bit larger for you. 1 over 4 over x squared and 1 plus 1 over x squared. Now I imagine a very large x value substituted, and I end up with 1 minus 0 over 1 plus 0, and this tells me I have a horizontal asymptote at y equals 1. So let's plot a dotted horizontal line, y equals 1. Okay. I think at this point I just need to substitute a few values. Negative 1 substituted here makes 1 minus 4. That's negative 3 over 1 and 1 are 2. So that's right there. At positive 1, I'm going to have the exact same behavior because the negative squared becomes just like the positive. So you see that I've got symmetry going on here. The same thing's happening in the negative direction as in the positive direction. Let's try 3. 3 squared 9 minus 4, that's 5. And 3 squared 9 plus 1 is 10. So this is like 1/2. I'm also going to get that here because the negative gets squared. So negative 3 half, positive 3 half. So all that remains now is to connect all the dots with a smooth curve and head toward the asymptote. So I'm going to start over here. I'm going to swoop in here and I'm going to kind of go like that. It's going to be a little bit like a curve down here at the bottom. And this is symmetric. This side should look just the same. And little arrowheads. And this is heading toward that boundary line. Let's check this one on the calculator. And I've got this one entered as the second graph. So I'm going to turn the first graph off by pushing equals or enter on the equal sign. And turn off the first one, just have the second one. And we choose graph. And sure enough, that's just like mine. This get cut off down here. It's not the best window. I actually should graph a little bit more negative values to see everything. Okay, we're on to the third one. We've got the horizontal, the vertical asymptotes, the x and y intercepts, the general shape, and we pick a few points. That's it. Alright, now this one's a little different. Notice that numerator. That numerator is x plus 1, x minus 1. You want to see this because these are common binomial factors that can be divided out. So really, this function simplifies to the line y equals x minus 1. But it's not quite that simple. This is not virtually this graph. It's just equivalent to it for the most part. But consider this. I have a division statement here. I no longer have it here. Over here, I can't divide by a result that makes this 0. That would be when x equals negative 1. It's undefined. Now that's true for the rational function. Over here, That gets lost in translation sometimes, so sometimes you need to be careful about this. What I actually have to do when x is negative 1, well, first let's graph this maybe. This is a line with a slope of 1, y-intercept of negative 1. So it's going to graph just like that. Now, when x is negative 1, back here, I actually don't have a value, so I'm going to make a hollow dot. This is called a hole, and it's a discontinuity. So it's a hole discontinuity. From here I'll connect the dots in this direction and make an arrowhead, and from there connect the dots, make an arrowhead. Now these are tricky on your calculator. Watch what happens if I try to graph this on my calculator. It's going to potentially let me down if I don't know what I'm looking for. So I've graphed the rational function as it was presented. I didn't graph the line. I choose zoom 4, and it looks just like a line. But what's going on here? See, the problem here can have to do with the resolution for the screen that you choose, different zoom values or windows, as well as this grid. So I'm going to turn this grid off. And when I do, something interesting is going to happen. Let's regraph it. Oops, I didn't turn it off for some reason. Let's try that again. Okay, there we go. I want the grid off. I graph it, and there it is. There's the hole. Now, be aware that if I choose zoom 6, I'm going to have trouble. Oops. Zoom 6 will actually not disclose it at all, because zoom 6 messes up the distortion of horizontal to vertical resolution values. So you need to watch out for that. I don't recommend using zoom 6 for graphing for that reason. Well, that's it. That's 3 good examples to give you an idea of how this works and what you need to look at.